Okay, so today we're going to review hybridization theory. Today's target is to understand how and why hybrid orbitals around the central atom form chemical bonds in a covalent substance. So, what do you think of when you hear the word hybrid? So when you think of the word hybrid, you oftentimes think of the Prius or a mule, where you're really blending either two animals or two ideas together, whether it be electrical and gas engine together. So hybrid orbitals in chemistry involves mixing as well. You're blending atomic orbitals. And so here you're blending either the S, P, D, F, and G, etc., depending on how many bonds the central atom can take on. So you're forming what is called equal energy hybrid orbitals. Hybrid orbitals explain the different molecular geometries formed by different molecules. Hybrid orbitals they're occupied by bonding electrons, which are called your sigma bonds, and they're also occupied by non-bonding electrons, also called your lone pairs. But one thing that doesn't occupy those hybrid orbitals are your pi electrons. They're actually on unhybridized orbitals. So the first thing we're going to do is we're actually going to practice, and then we'll understand what happens underneath the surface of a hybrid orbital. So if you look at this, number one, you look at the central atom, and in the central atom you're going to need, because you have two sigma bonds, those are where the hybrid orbitals are going to occupy, you're going to need an s orbital and a p to hybridize to make the two hybridized sp orbitals for the sigma bonds. One bond will take place with the hydrogen. The other sigma bond will be taking place with the nitrogen. The other two bonds are called pi bonds, and those are on unhybridized orbitals of carbon. So it might be on the 2px or the 2pz, for instance, these two pi electrons. And again, they're on unhybridized orbitals. Whereas the bonds that you see here between carbon and hydrogen are on hybridized sp orbitals, and the carbon and nitrogen is also on the sp orbital. Now we go to number two. You count how many hybridized orbitals necessary for around the central atom. So nitrogen has one lone pair, which requires a hybridized orbital. Here's another sigma bond, which requires a hybrid orbital, and then another sigma bond between the nitrogen and nitrogen. And so it needs three hybrid orbitals. And so you'll have to mix one s and two p's to make three sp2 hybrid orbitals. Okay. Now we go to number three. Number three, you see 1, 2, 3 hybrid orbitals that you would need. And so this would again be the mixing of one s and two p, giving rise to the sp2 hybrid orbitals around nitrogen. Number four, there are three hybrid orbitals needed. And so to have three, you'll mix one s and two p's, giving you sp2 hybrid orbitals. Here you have 1, 2, 3 hybrid orbitals necessary for the oxygen, giving rise to the sp2 hybrid orbitals. Now here you have 4. So 1, 2, 3 are your sigma bonds, and then the lone pair is another hybridized or another orbital you'll need for to be hybridized. So there's 4 total. So you'll need to hybridize one s and 3 p's to make what is called the sp3 hybrid orbitals. Let's go to the next one. Let's look at this set and see if you could do it yourself. For number 7, you'll need to make sure that you are hybridizing each of the carbon atoms, and so you're finding hybrid orbitals for each of the carbon. So I'll give you about 2 minutes to be able to work through each of these, okay? Or 3 minutes. Okay, so let's take a look at number 7. That was in 3 minutes, but given the time, we'll have to look at this together. So here we have carbon. Carbon needs 4 hybridized orbitals, so it's sp3 around this carbon, and then it's also 4 needed for this carbon, so it's sp3 around each of the carbon atoms. Here you need 4, so it's sp3 as well. And here you have 2 atoms that have different hybridization. So this carbon needs sp3. This oxygen needs also sp3 as well. So it's sp3 around carbon and oxygen. When you get down to this right here, sulfur is going to need 1, 2, 3, 4, 5. It needs 5 hybridized orbitals, which means now you're going to have to expand outside of the octet, which means you're going to need a d orbital. And that empty d orbital is necessary to be hybridized in order to accommodate the 4 sigma bonds and the 1 lone pair. So this is going to be 1 s, 3 p's, and 2 d orbitals. Or sorry, 1 d orbital that would be required to be hybridized, giving rise to 5 hybridized orbitals. So it's called sp3d. This one you'll need 6. So if you notice 6 around sulfur, so 6 hybridized orbitals are necessary. So this would be sp3d2. And the same with this, sulfur here in the number 12 also requires 6, so sp3d2. Let's take a look at the next slide and the practice for the next slide. Here you need 1, 2, 3, 4, 5. So you need 5 hybridized orbitals, so it's sp3d. And this next one, in this central atom, you need 1, 2, 3 lone pairs, 4, 5. So 5 sigma bonds, and so you're going to need 5 hybridized orbitals, and so it would be sp3d. Now you look at this structure around the central atom, and this central atom needs 1, 2, 3, 4, 5 sigma bonds, and then 6 for the lone pair. So it would be sp3d2. So let's make sure we understand why these hybridized orbitals occur. So carbon, according to the quantum mechanical model, carbon's orbital notation looks like this. Technically, there should be only 2 bonds in carbon. However, we've seen the existence of many more bonds, 4 bonds specifically around carbon. And in methane right here, you'll see that 4 bonds are attached to each of the hydrogens around the carbon. So this here doesn't accommodate for the fact that there's 4 bonds made around the carbon. You would imagine there would be 4 unpaired electrons, as you see down here. So what we'll need is we'll need to hybridize orbitals to make these 4 unpaired electrons equal in energy as well, so that we know that if we break each of these carbon-hydrogen bonds, it would require the same amount of energy to break each of these carbon-hydrogen bonds. So the 4 orbitals that we'll need will require us to hybridize 1 s and 3 of the p orbitals. Now notice there's the px, the py, and the pz orbitals that you would hybridize on the valence shell. And in doing so, now you've created this new hybridized orbital, and so how we label this new hybridized orbital is sp3, and we have 4 of the unpaired electrons that account for the 4 bonds that carbon can make. Here you see sulfur. Sulfur, as it would suggest here, would only make 2 bonds, only, and always. And so if you look at this here, the 2 bonds account for what you see here, according to the quantum mechanical model. But really, sulfur actually makes 6 bonds in sulfur hexafluoride. And because of that, we need to have a structure that accounts for the 6 possible bonds that sulfur can make. So we must hybridize enough orbitals to make the 6 hybrid orbitals. So we'll need to hybridize 1 of the s, 3 of the p's, and of course 2 of the s. And when we do that, we have a new hybrid orbital called sp3d2, and leaving us with 6 unpaired electrons that are situated equally around the sulfur atom, giving it rise to this shape called an octahedral shape. Okay, so now imagine this is sulfur's 6 valence electrons, and each of the fluorine atoms will occupy each of these still unpaired electrons that are on these hybrid orbitals. There's 6 of them. Okay, so imagine that. Now notice that because sulfur has an expanded octet, it moves into the d orbital when you hybridize it. Now when we get into pi bonds in hybridization, pi bonds are an unhybridized orbital. If you notice this carbon has an unhybridized py orbital. And so what happens is the electron that's on each of these carbon are going to bond covalently. But it's on unhybridized orbital that these pi electrons are going to bond. And these electrons are delocalized between the atoms, which means they move all about these unhybridized orbitals. Whereas these sigma bonds are actually on localized, they're localized between the atoms that are bonded. And so that's why they're on hybridized orbitals. Now if you look at carbon has 1, 2, 3 necessary hybridized orbitals. And so we need to hybridize the s and one s and 2 of the p's to make those 3 hybridized orbitals. And the same goes with this carbon right here. So hopefully you can see how the hybridized orbitals bond, and then of course how the unhybridized pi electrons bond with each other between the 2 atoms that have unhybridized orbitals. Here you have ethine, another example of showing that's the sigma bond right here, and of course the 2 unhybridized orbitals, one at the 2py orientation, and then the other one which is the 2px. They're going to be bonding, which means there's 2 pi bonds. And if you look at the bond between the 2 carbons, the 2 carbon atoms, there's 2 pi bonds and of course 1 sigma bond between the 2. And so the sigma bond is on a hybridized orbital. Just likewise, this carbon-hydrogen bond is a sigma bond on a hybridized orbital, so you'll need to hybridize 1 s and 1 p to make an sp hybridized orbital. Now notice how the 2 spots for the unhybridized will be occupied by the carbon. So one of the unhybridized orbital, which is the 2py, will be occupied by the other carbon. And then the same other carbon atom will occupy this 2pz spot, which gives them the the triple bond. Okay. Now we go to lone pairs. Lone pairs actually occupy hybridized orbitals. That's why lone pairs are involved in causing that extra repulsion to make the geometry, or to conceive this geometry of a trigonal pyramidal for this substance called ammonia. And so when you hybridize ammonia or nitrogen's orbitals, you'll have to hybridize 1, 2, 3, 4 needed hybrid orbitals. And so you